Dimensionality reduction. Dimensionality reduction refers to the technique of reducing the number of input variables in the training data. High dimensionality might mean hundreds, thousands, or even millions of input variables. Fewer input dimensions often mean correspondingly fewer parameters or a simpler structure in the machine learning model, referred to as degrees of freedom. A model with too many degrees of freedom is likely to overfit the training dataset and therefore may not perform well on new data. It is desirable to have simple models that generalize well and in turn input data with fewer input variables. This is particularly true for linear models where the number of inputs and the degree of freedoms of the model are often closely related. Dimensionality reduction is a data preparation technique performed on data prior to the modeling. It might be performed after data cleaning and data scaling and before training a predictive model. As such, any dimensionality reduction performed on training data must also be performed on new data, such as the test data, validation data, and the data when making a prediction with the final model. Dimensionality reduction is a transformation of data from higher dimensional space into a lower dimensional space so that the low dimensional representation retains some meaningful properties of the original data, ideally close to its intrinsic dimensions. Dimensionality reduction plots. We will perform a dimensionality reduction techniques to plot the observation in two dimensions. We will be using two techniques, the principal component analysis and the TSNE technique. The principal component analysis is a technique that relies on obtention of the eigenvalues and eigenvectors of the data matrix and tries to provide a minimum number of variables that keep the maximum amount of variance. The TSNE stands for the T-distributed stochastic neighbor embedding, which is a probabilistic technique particularly well suited for visualization of high-dimensional datasets. It minimizes the divergence between two distributions, a distribution that measures pairwise similarities of the input objects and a distribution that measures pairwise similarities of the corresponding low-dimensional points in the embeddings. To perform this, we will import the required libraries and packages, and then we will get features and labels and plot them. After obtaining the labels and features, we will unify the training and the test sets The initial shapes of these are as follows. That is 1891 for the training set and 334 for the test set. We then define a function that comprises the whole virtualization process. We create a model and fit and transform the features in it. We then put them into a data frame. Now we have to paste each row's labels and its meanings to convert the labels arrays to DF, that is data frame. We get the labels names and map the labels, and then we perform the plot. Dimensionality reduction with PCA. Let's plot the PCA model results. From the PCA model, this is the graph we formed for PCA decomposition, where the red spots refer to the technology category, the pink spots refer to the political category, the dark blue spots, which is seen on the left side of the graph, refers to the business category, the green spots refers to the sports category, and the light blue spots on the right side of the graph refers to the entertainment category. We then perform the dimensionality reduction with TSNE, plotting the graph for the same. We can distinguish the five categories more clearly in this graph, where we have the red spots for technology, pink spots for politics, dark blue spot for business, green spot for sports, and light blue spot for entertainment. The TSNE decomposition helped us in clearly distinguishing the five categories, whereas the PCA model had the five categories overlapping one another, hence it was difficult in distinguishing each other. We can see that the TSNE decomposition works much better on our data than the PCA model or the PCA decomposition method.